I shared about the surveillance system that I've built on the Raspberry Pi platform to monitor the environs of my home and alert us about possible intrusions by a person or animals. At the heart of the system is a contemporary Raspberry Pi 4 that acts like a server, or more appropriately, a broker, to which a network of surveillance units can publish information, including images, that it aggregates and displays nicely in an image gallery. Any device, such as an Android phone, can then receive alerts, such as when motion is detected, and access surveillance footage by subscribing to any of the topics by which the broker organizes incoming information. In the basic setup, I have used the MQTT broker from Mosquito software and coded ETL jobs in Node-RED. ETL, extract, transform, and load information into a central image gallery. It has a bit of a James Bond feel. To give it even more of a James Bond feel, I want to give the system some smarts for motion and object detection. In a previous video, I described the algorithm for motion detection. We looked at the science, the implementation in code, and the performance, the results. Here, we will move on to the science, the software, and the performance of object detection with deep learning. In the late 1990s, as a machine learning practitioner, we coded neural networks from the ground up in programming languages like C and C++, a rather tedious and laborious task. When I complained about this to my supervisor, he would tell me how in his day, programs were a deck of punch cards with instructions in assembly language for the computer, and how it was his job to take this deck of cards to a computer in the basement of the university facility where he worked, where it took up all the space. So much for that. So it's pretty amazing that in 2020, we can run deep learning algorithms on a credit card sized computer. The Raspberry Pi fits in a box this size. And while this is exciting, there are challenges along the way that can make this a daunting task. So in this session, I show how to get the job done using TensorFlow Lite, a framework for deep learning from Google. I love making salads. I go to the supermarket, Whole Foods, pick the spinach, the lettuce, the cucumbers, the tomatoes, the romaine. I bring them home and make a salad following my own recipes. Machine learning, deep learning, is like that. We pick the ingredients that we need off the shelf and use them in our own recipe. What are these ingredients? These are software libraries for programming languages that are popular among data scientists like Python, R, even JavaScript. And these make available algorithms, very powerful algorithms for deep learning and related tasks to the programmer. And because there is more to deep learning than just the algorithm, how do you prepare data? How do you present it to the algorithm? How do you train your models? How do you assess model performance? And then how do you deploy the model when it is ready? These libraries are developed under the auspices of a framework that addresses all of these concerns. Two popular frameworks at the top of the list are TensorFlow from Google and PyTorch. Ordinarily, we would use the full-fledged TensorFlow framework. However, frameworks such as these are computationally hungry and require special hardware, like the microprocessor cores found in gaming stations to run. Rendering the cool, lifelike graphics that make these computer games interesting involves a ton of linear algebra. And these GPUs, graphical processing units, make these operations run much faster by parallelizing them. Therefore, deep learning algorithms, which also involve a ton of linear algebra, like matrix multiplication with very large matrices, we find that the marriage of deep learning and GPUs is a happy one. But not so the marriage of deep learning and ARM, the microprocessor architecture of the Raspberry Pi. In fact, TensorFlow was off limits for the Raspberry Pi for a really long time. So to run TensorFlow on the Pi, we need a strategy in 3 steps. So let's look at these 3 steps. Number 1, Google engineers have created a less resource-hungry version of TensorFlow called TensorFlow Lite. Use TensorFlow Lite. Number 2, even TensorFlow Lite may quickly overwhelm the computational resources of our Pi. This is especially true for older versions of the Pi before the Raspberry Pi 4, which has a beefed up microprocessor and more options available for RAM, that part of the memory that is in use while these linear algebraic operations are in progress. But even so, TensorFlow Lite can quickly overwhelm the resources of our Pi. So use a trimmed down version of TensorFlow Lite called the TensorFlow Lite runtime. Now this pared down version has only one class, and that is the one that we need for making predictions with a convolutional neural network with learning. So if our model can only make predictions, then how are we to train the model? Which brings us to number 3. We don't train the model. Instead, we use a pre-trained model. And there are many such models, deep learning models, made available freely by the open source community. They have names like MobileNet, Coco SSD, VGG, AlexNet. They are normally distributed as flat files and have versions for TensorFlow Lite. So use the pre-trained model that best serves our purpose. And if we really need to train the model for a task that it will not already do, let's see about that next. And if we find ourselves needing to tweak a pre-trained model before using it, then what? So this option is based on a technique called neural transfer learning. And what this is it allows us to start with a pre-trained model and adapt it to a new task, which is usually a specialized version of a task that it can already do. This requires only a fraction of the data that were used in training the original model. You can do this right now using Teachable Machine from Google, which makes available a select few model architectures. You can tweak the model using neural transfer learning in your browser without writing a single line of code. After you're done and satisfied with the model's performance, export the flat files for TensorFlow Lite that have the updated model parameters and related metadata. And if this will not suffice, then what? We can always train our TensorFlow models in Google's cloud using one or more GPUs, free or through Google's subscription model, and then export to a TensorFlow Lite version, and then use that in our code. So there are options available and there are trade-offs to make. But enough talking, let's jump into the code. Here is my Jupyter notebook on GitHub. It is named Surveil. Use the TF Lite runtime. This library has only one class, interpreter, which we use for prediction. We cannot use it to train the deep learning model. So we will work with the MobileNet convolutional neural network architecture. MobileNet can classify images into 1,000 categories with the pre-trained model. We can use TensorFlow Lite runtime with other convolutional neural network architectures as well. We are not restricted to MobileNet. And so which architecture to use and what parameters to use to flesh out the model with that architecture? So we need to configure the interpreter to tell it that. And we do this using flat files that we download. These flat files are made available by Google as well as the open source community. We will come to this step later. Use PIL for image analysis, chiefly for sizing images to condition them to be ready for presentation to the convolutional neural network, to the deep learning model. We can use OpenCV, and again, that is a bear to install and use on the Raspberry Pi. PIL is less resource intensive. And as far as the Raspberry Pi is concerned, works more reliably, in my opinion. So let's go with PIL and import the image class. Use NumPy chiefly to capture the contents of an image for presentation to the convolutional neural network in the way that it expects, the way that is compatible with the selected architecture, which is MobileNet. And use PyCamera to take pictures for classification. There are a few other libraries that will help us along. Time for timestamps, OS for working with file paths, IO is joined at the hip with PyCamera for taking pictures, and Matplotlib in order to show the pictures and the results in our Jupyter notebook. These are the ingredients that we will be cooking with today. There are 4 steps to this image analysis challenge, this computer vision with deep learning. Step number 1, set up the convolutional neural network. Specify the architecture and load the corresponding model parameters. We do this using flat files that we download off the web. The links are here in this Jupyter notebook. This is step number 1, setup the CNN. Step number 2, set input. Take a picture, condition it, and present it to the convolutional neural network. The convolutional neural network expects an RGB image of fixed width and height. We'll need to address that with PIL and then convert the image, the picture, to a NumPy array of the right dimensionality for presentation to the CNN and then feed it to the CNN. This is step number 2, set input. Step number 3, make prediction. So now that we have configured the neural network and we have fed it the input, we wanted to make a prediction and classify the image or detect objects in it. This is where the algorithm earns its paycheck, in a manner of speaking. It is also the simplest step to implement in code. This is step number 3, make predictions. Now that we have a prediction, we need to conclude from that. This brings us to part number 4, get output. The results of analysis in the raw form consist of probabilities for each class label. Remember that MobileNet can recognize 1,000 objects. Each one of these 1,000 class labels has a corresponding probability, a likelihood of success, basis which we rank order the labels and select the top 5 or the top n. This is step number 4, get output. Now we'll look at each one of these 4 steps in detail, diving into the code. Step number 1, part 1, set input. So we work off 2 files that we have downloaded already and saved to a local folder. One of the files, the file with the extension .tflite, has the CNN architecture and the corresponding model parameters. The other file has the extension .txt, and it contains all of the class labels for the objects that the CNN can recognize. We check that these files exist at the specified location and confirm that. Open the file, the text file that has the class labels, and examine the first few entries: goldfish, white shark, tiger shark. Lots of animals in there. And the meat of this step, this part, is calling the allocate tensors method of the interpreter after pointing it to the tflite file. So at the end of this step, we now have a CNN that is pre-trained and ready to use. Let's feed it an image in the next step. Step number 2, set input. So we need information about how the CNN expects input. There are two very handy methods of the interpreter class, object of the interpreter class: get input details and get output details. Get input details tells us more about the input image and how to present it to the CNN. We call this method and save the results in the variable input underscore details. Get output details tells us more about the output prediction and how to access it. We call this method and save the results in the variable output underscore details. Input details we will use in this step. Output details we save for use later in step number 4 when we are interpreting the results and drawing conclusions. In this step, input details yields one vital piece of information about the expected input, which is the image size, the height, and the width. For MobileNet, we see that the CNN expects images of size 224 by 224 in 4 dimensions. Why 4 dimensions? Height by width, that's 2. RGB for the color channels, that's another dimension, so 3. What's the 4th dimension? Input can be not only one image, but a series of images, each 3-dimensional. Each unique image is indexed by axis 0, hence 4-dimensional. Since we are dealing with one picture at a time, we'll need to artificially inflate the dimensions to 4 to satisfy the convolutional neural network. This is where NumPy comes in very handy to add another axis at position 0, aka inflate the dimensions to satisfy the CNN. But first we have to take a picture. Let's see about that. Function takeSnap takes a picture of the specified width and height. It configures the Pi camera settings such as rotation, resolution, and now that we know the correct size, the width and the height of the image for the CNN, we resize the picture after converting to RGB. These with PIL image class. This function returns the picture as a PIL image. The code here is boilerplate for working with the Pi camera using the IO class. Also, showSnap shows the picture returned by takeSnap. It accepts as argument the picture with an optional title and subtitle, which are displayed above and below the image. It turns off the axis ticks and then shows the image size in the subtitle if no subtitle is provided. Uses the show method of matplotlib. Take the snap, size 224 by 224 RGB as expected by the CNN MobileNet, and then show it in the Jupyter notebook. Let's title it raw footage. Here is the image, the raw surveillance footage from the Pi camera. Now what remains is to feed this image to the CNN, and that is 2 lines of code. First, use NumPy to inflate the image dimensions by adding a new axis at position 0. So this will satisfy the CNN. Second, pass the image to the CNN using the setTensor method of interpreter. This method takes 2 inputs. The first is the index, the location where the image is stored in how the interpreter manages its internal storage. Yeah, we get this location from input details. And the second is the image itself, now shaped appropriately for the CNN. Height and width are 2 to 4 pixels, and the object is a 4-dimensional array. Notice that we use getInputDetails method to obtain information that we will then use with the setTensor method. Likewise, later on, we will use the getOutputDetails method of the interpreter with the getTensor method when we are interpreting the results. This is a great pattern to keep in mind to simplify our understanding of the code as we firm up our mental model of using TensorFlow for computer vision and image classification. Get input details, pair it with setTensor, get output details, pair it with getTensor. Okay. So now we are ready for the show to roll and make a prediction. Step number 3, part 3, make a prediction. Now this is 1 line of code and there is a lot of heavy lifting going on. We call the invoke method of the interpreter and the prediction is done. What's the heavy lifting going on? Linear algebra, matrix multiplication, applying a filter bank to the image through a series of convolutions. What is a convolution? A convolution is a mathematical operation that reveals patterns in an image. And so the first set of convolutions reveals primitives in the image. Primitives. Think of caveman drawings of animals, zebra, lion, buffalo, events, harvest, hunt. They are structurally simple, yet rich in meaning. So the first set of convolutions reveals primitive structure in the image contents. Now subsequently, convolutions reveal the structure underlying shapes and textures based on these primitive patterns, how these are composed into shapes and textures. And this goes on until the classifier can perceive recognizable objects based on the shapes and textures that they are composed of. And so this is all part of the CNN's training process, starting out with primitives and adding layer after layer of meaning through convolutions that reveal progressively more complex structure, that progressively reveal more complex structure. And with prediction done, it is now time to examine the results and draw conclusions. Step number 4, get output. Here we use the get tensor method to get the raw results of analysis of prediction. Use output details to set the index where this information is located. Squeeze is a NumPy method that will get rid of any dimensions that do not contain information. So these extra dimensions. Remember, we had inflated the input image to make it suitable for feeding to the CNN. We are squeezing the output to get rid of any axes devoid of meaning by the same token. We then denormalize the output to get the success probabilities for each classification label. And then what we need is to find the top n, here the top 5, the top ranking results. Note that we have used the NumPy method arg partition to get the top ranking values from the output array. We want to use this method when dealing with long arrays, lengthy arrays, such as this array output that has the success probabilities for 1000 items, for 1000 objects. Now note that the success probability is a value between 0 and 1, 0 being the least likely and 1 being the most likely, 100% certain. Arg partition accepts two inputs, two arguments. The array from which we want the top ranking values, and we have reversed the sign because we want the results in descending order of success probability. And the second is the number of the top ranking values that we want. So arg partition will only worry about getting us these many top ranking values, and it will not worry about the remaining values in the array. And that is what makes it efficient. And it will then return an array of the same length as the input array with the indices of the top ranking values on the left. So if we specified top 5 values, the first 5 elements of the returned array, here we have called it ordered, we have named it ordered. So these first 5 elements of the returned array are the indices where these top 5 values are at. And in no particular order, mind you. Slice the returned array to get the indices of the top ranking values. Of course, ignoring the rest of this array, which doesn't signify any result of consequence. And then use each of these indices to get the class label and the corresponding success probability as a tuple. So in conclusion, we have an array of tuples with the top ranking results, however many we specify, 5, 7, 15, what have we. In this example, it identified my table, which features rather prominently in the picture as a pool table with 73, 74, almost 75% probability. What do you think of that? And as you can see, these results are in no particular order, as long as they are the top 5 ranking results. Now, this behavior of the arg partition method sometimes feeds into the perception, sometimes leads to this method being perceived as having a counterintuitive behavior. But it is the most appropriate method to use when dealing with lengthy arrays to extract only the top ranking results. So this concludes the discussion of the four-step process. In the rest of the Jupyter notebook, I have packaged the code into four functions, one for each step, roughly speaking, in the process. Load labels corresponds to step number 1. Set input tensor, step number 2. Predict, step number 3. And report top matches corresponds to step number 4. I've also written a wrapper function, classify me, to implement all of these steps, tie them together to classify an input image of the right width and height and in RGB format. So these serve as exemplars for a module with the class object detector for use in the surveillance system. So that's coming up next. In conclusion, we have tested an approach and for offline object detection on the Raspberry Pi, because it may not always be connected to the internet. And so offline object detection with the code running on the device is important. We've proved that this approach works using PIL to work with image data instead of OpenCV, which is challenging to work with on the Raspberry Pi. Using TensorFlow Lite runtime instead of the full-fledged TensorFlow library. And as a consequence of that, using pre-trained models. And also that if the pre-trained models don't go far enough, then we have options such as using Teachable Machine from Google to tweak the models to adapt them for our purpose. So with this confidence in our approach, we will now proceed to write a module with an object detector class for use in our surveillance system. That's coming up next.